Welcome. As the solar water heating systems become popular, the number of collector manufacturers also increased. So on the background of increased number of collector manufacturers in India, some standard is needed for testing the collector. So testing is needed to correctly estimate the performance of collector over its life. To facilitate, and then testing is also needed to facilitate system design at any location with given set of tested collectors. For example, a designer sitting in Hyderabad, he wants to design a system against a hot water demand of 10,000 liters per day. Now he is intending to use some XYZ company collectors. Now if those XYZ company collectors are tested and those results are known, then with the help of those test results, he can design the system, he can size the system and then plan the economics accordingly. So testing is essential in that case. So it will be helpful for the designer to design the system. Therefore, Bureau of Indian Standards has prescribed the testing method as per 12933 part 5. We have already seen in our earlier lectures about this standard. Internationally, the most well-known standards, there are two standards. One is ISO, International Standards Organization, ISO 9806-1, which was presented in 1994, and then ASHRAE Standard 93, which is revised in 2003. So these standards, now what is the use of these international standards? Suppose a manufacturer in India wishes to export his collectors to the other countries, then he must test those collectors either as per ISO or as per ASHRAE standard. So these standards are also important as far as export of collector is concerned. Now these standards are applicable to non-concentrating as well as concentrating collectors. Now the figure shows the schematic of closed loop test setup for thermal performance of liquid flat plate collector. So this is a closed loop. So heat transfer fluid is circulated. So this heat transfer fluid may be many times water, but it can be any fluid, maybe any oil. Heat transfer oil also can be used in this circuit. So the circuit is a closed circuit. So there is no outlet for the heat transfer fluid to come out. Now the working of this setup is the collectors or a collector to be tested is installed at a certain angle beta, and then a pyranometer is fixed which is parallel to this plane of the collector to measure the beam normal radiation. Then a windscreen is provided in the vicinity of the collector to measure ambient temperature. A cup type of anemometer is used to measure the wind speed in the vicinity of the collector. Pyranometer measures the solar radiation. Now this liquid flat plate collector is connected to the circuit through a pipeline. So it has an inlet and outlet. Now at inlet there is a thermocouple or resistance temperature device provided to measure the temperature of fluid entering the collector here. And then at the outlet again a thermocouple or any RTD is provided to measure the temperature of the fluid leaving the collector. Pressure gauges are installed at the entry and exit of the collector to measure the pressure drop in the fluid over the passage of the collector. Then a flow meter is used in line towards the inlet to measure the flow rate to the collector. That flow rate is m dot kg per second. Now preceding flow meter or before the flow meter there is a pump. This pump provides the motive force. This pump helps the fluid to be circulated through the entire circuit. Now on the discharge side of the pump, here there is one bypass valve provided. Now if a testing personnel wishes to vary the mass flow rate flowing through the line, then he will change the opening of the bypass valve. So due to that, what will happen? The discharge which is going to the flow meter will change. So why this type of arrangement is provided? Because this will prevent the back pressure building up on the back line. Okay, imagine that instead of this bypass valve, if a single flow control valve is provided here, and then the valve is in the first case it is open, pump is discharging under certain pressure. Now the personnel wants to reduce the discharge. What he will do? He will close the valve. So when he closes the valve, a pressure builds on the pressure builds in the back side of the pipe, and the pressure goes on building, and that damages the pump valves and fittings. Same thing will happen if the discharge is to be increased. There will be sudden increase of the pressure that may damage the line here. So to reduce that effect, a bypass valve is used. So bypass valve can be opened widely, or it can be closed. It can be closed to reduce the discharge. So this circuit is used for controlling the discharge to the collector. Now a storage tank with electric heater is provided to vary the temperature of fluid entering the collector. Now these tests are prescribed at different fluid inlet temperature. So the desired fluid inlet temperature may not be obtained with the solar radiation falling. So if we want to design the fluid inlet temperature as per the requirement, then this storage tank and electric heater will serve the purpose. For example, in normal case of radiation, the fluid inlet temperature with water may not exceed 60 degrees Celsius. But then that limits the test range. But this collector has to be tested. If the collector is needed to be tested at TFI 75 degrees Celsius, then in that case, the 75 degrees Celsius of water is heated here, and that water is supplied, so that at TFI 75 degrees Celsius, what would be the performance? So that is the purpose of the storage tank, which is provided with an electric heater to vary the temperature of the fluid entering the collector. Now the fluid is circulated, it moves through the flow meter, through pressure gauge, and through this RTD device to the collector. It is circulated to the collector, it receives the heat when solar radiation is incident, and then it comes out passes through this pressure gauge, and then in absence of this device, the hot fluid would be supplied again to the storage tank, which is not a desired case. In that case, what happens, over its continuous operation, the temperature in the storage tank will go on building, and then there will not be any control on the inlet fluid temperature. So there must be some means to get rid of the heat, to remove the heat from the circuit. So this heat exchanger, which uses cooling water, which is used for removing heat from the circuit. Now cooling water is circulated through these coils and heat is removed. So if we vary the mass flow rate of cooling water, the rate of extraction of heat can also be changed. So this is the experimental setup. It is just the description of the experimental setup. So collector to be tested is installed with a requisite tilt. I am just reading this for the sake of download, those who want those students or faculty who want a write-up of the test setup, for them this write-up is written. Otherwise, I have already explained this write-up in a previous thing. So a pump circulates the collector fluid through the pipeline. On the discharge side, a bypass valve is provided to control the TFI, flow control. A flow meter is installed before the collector inlet, which measures the m dot to the collector, and then temperature of the fluid entering the collector TFI and leaving the collector TFO is recorded using thermocouple or RTD. Okay, so a storage tank with electric heater is provided on the suction side of the pump. So on the suction side of the pump, storage tank and electric heater is provided. A cooling coil is provided here to extract the desired amount of heat from the circuit. Now the purpose of undertaking the thermal performance test is to determine performance characteristic collector efficiency factor. Okay, so this is as per Indian standard 12933, this setup. This is a thermal performance test. So why to carry the thermal performance test? The thermal performance test is carried out to decide the performance characteristic of the collectors. Which are the performance characteristic of the collectors? First is collector efficiency factor, FR tau alpha, and loss coefficient, that is FRUL. So these two parameters, if we determine for a collector, that becomes the characteristic of the collector. So FR tau alpha and FRUL describe the characteristic. They characterize the collector. Okay. Now what is and then these characteristics are determined over a wide range of operating temperatures. That is by varying the fluid inlet temperature, by varying the solar radiation intensity. Solar radiation intensity automatically varies. Then incidence angle also is varied. So at different incidence angles, TFI and the radiation intensity, what is the average value of these characteristics is to be determined. What is the procedure then? The collector shall be tested. Now this procedure is prescribed by the Indian standard. Okay, so the collector shall be tested under clear sky condition and close to the solar noon. Why close to the solar noon? Because the angle of incidence near the solar noon is less. So the test must be conducted within the range of incidence angle of 15 degrees. So near solar noon the incidence angles are less. Now at this time near the solar noon, the predominant component of solar radiation is also beam component. So if we install a pyranometer along the plane of a collector, it will measure the beam radiation, normal radiation intensity. Okay, so on any given day, data is recorded under steady state condition. So steady state condition, there are parameters given for determining the steady state. How do you assume the steady state? For example, if solar radiation intensity is not varying in the range of 50 watt per meter square, then you can say that the steady state is achieved. If the temperature of water is not changing, say in plus minus 1 degree or plus minus 2 degrees Celsius. So as per the Indian standards, that those parameters are given and their ranges of change is also given. So if the parameters remain in those ranges, we can easily assume that the test is taken in steady state condition. Okay, and then these tests are conducted for fixed values of flow rate, that is m dot, and TFI, that is collector fluid inlet temperature. Now for each set of fixed values, it is recommended that an equal number of tests be conducted symmetrically before and after solar noon. For example, if we plan 4 tests in a day, so if 4 number of tests are planned on a single day, then the schedule, the designer or the test personnel must plan the schedule like this. First test will be taken at 11 o'clock, then second will be at 11:30, then third will be at 12:30, that is 12 is a noon, then 12:30 half an hour after noon, and then 1 hour after noon. So two tests are before noon and two tests are after noon. These timings are local apparent times, LATs, okay, because standard times doesn't have any meaning here. Why this symmetry has to be maintained? Because due to the transient effects, change in the temperature due to change in the parameter. So any inaccuracies which are coming due to these transient effects is eliminated because of the symmetry. We can very well cross check, because 1 hour before noon, the readings, the set of readings which we get must be more or less similar to the readings which we get 1 hour after the noon. So the readings at 11 o'clock and 13, they must have some logic in that. So any bias which comes because of the transient effects is eliminated in the symmetry. Now if such data is recorded for 4 inlet temperatures on different days, then a total 16 data sets are obtained. For example, 4 tests, 1, 2, 3, 4, 4 tests per day, and then for 4 inlet temperatures, and then on different days, then total 6. So if we take these readings for 4 days, then total 16 data sets are obtained. So this is the minimum number of data sets which are recommended by the Indian standard. Now during the testing, following measurements are made. Those measurements are water flow rate, m naught, temperature of water entering and leaving the collector, that is TFI and TFO, solar radiation incident on the collector plate, that is IT. Actually it reads IB and then we have to calculate IT. So solar radiation incident on the collector plate, IT, we can read. Then ambient temperature, TA, ambient, and then wind speed, V infinity. Collector area AC and absorber plate area AP or aperture area AP are measured prior to the test. Now instantaneous efficiency of the collector can then be determined with the following equation, that is efficiency is equal to useful heat gain rate QU by AC collector area into IT, which is also equal to m dot Cp. So mass flow rate of water into Cp of water, or mass flow rate of heat transfer fluid circulated through the setup, and then Cp of the fluid, and then our collector fluid outlet temperature, collector fluid inlet temperature. So temperature difference again with the same denominator is carried here. Okay, so with this we can find out the instantaneous efficiency of the collector. So this instantaneous efficiency, useful heat gain rate, is also expressed in terms of Hotel-Villiers equation. So useful heat gain rate QU by AC upon IT. So instantaneous efficiency expression can also be written in this form using Hotel-Villiers equation. So this expression is this, AP upon AC. While calculating QU using Hotel-Villiers equation, we use the aperture area. Okay, so this is aperture area by collector area. Collector area is from denominator here, and then FR tau alpha average minus FRUL TFI minus TA upon IT. Now a test sheet or observation sheet of a typical test setup looks like this. So the sheet will have, or somebody can plan the sheet in this way also to be in a more organized manner. So a single sheet for a single day, or a single sheet for a single session of 16 sets. So location, for example, say Nagpur, latitude maybe 19 point or whatever, latitude, longitude, date, declination, standard time longitude, collector tilt, collector area, AC and absorber area. So these details are entered here, and then the observation table will have following parameters. First is serial number, then 1, 2, 3, 4, 5 like this, 16. Then time of the test, or maybe serial number 1, 2, 3, 4 for different TFI, then second day. So day 1, day 2, day 3 also these tables can be made. Now time of the test for example say 11 o'clock LAT. Then IT watt per meter square, which is read and calculated from the parameter. mass flow rate measured from the flow meter, kg per second. Collector fluid inlet temperature, collector fluid outlet temperature, ambient temperature, wind speed. Then useful heat gain rate we can calculate as mCp TFO minus TFI. So this is mCp is known. Cp of the fluid this data can be read from the data tables, and then TFI TFO is known. So QU can be found out. Now efficiency can be determined using the expression m dot Cp TFO minus TFI by ITAC. So efficiency eta I can be calculated here, and another parameter TFI minus TA divided by IT into bracket AC upon AP. This parameter has to be evaluated. That we will see why this parameter is needed in the next on the next page. Okay, and then the collector characteristic calculated for that session of the test, that is FRUL and then FR tau alpha. So now here the values of FR tau alpha average and FRUL are essentially constant. So in this expression we can say here, so we can imagine this equation to be y is equal to mx plus c. So this is FRUL TFI minus TA upon IT is x. Okay, and FRUL and FR tau alpha are constant. Okay, so the values of FR tau alpha and FRUL are essentially constant. So if the values of efficiency are plotted, against TFI minus TA by IT into AC upon AP, so if they are plotted against this, we will get these type of data points here. Okay, so this point, so out of these tests, so number of readings we can take, and then this data you can plot like this. So the points will look like this: test number 1, test number 2, 3, 4, 5, 6, 7, 8, 9 tests you conducted. So you get 9 data points. So these data points, a single order polynomial is fitted to these data points, then you get a straight line with negative slopes. Okay, so you get a fit if the data is fitted with a straight line, you will get this type of straight line with negative slope. Now you can imagine the equation of the line to be not what we imagine. The equation of the line is y is equal to mx plus c. Okay, and now we have this expression eta I is equal to minus FRUL. We have rearranged the equation here. FRUL TFI minus TA upon IT AC upon IP plus AP upon AC FR tau alpha average. Now you can see here mx. So this is m, this is x. So this is x. And then C is this AP upon AC FR tau alpha average. So m is what? M is the slope of the line, and C is the y-intercept of the line. Now y here is the instantaneous efficiency, and m is FRUL. So here m is FRUL and C is FR tau alpha average, AP upon AC. In most of the cases, if AP and AC are separately given, then you can use AP upon AC. If in absence of the mention of AP and AC separately, you can take the value of AC, and in that case AP is equal to AC, and then AC becomes 1, and in that case C becomes FR tau alpha average. So here, so you can get the character, you can calculate by fitting this data, you can calculate the value of FR tau alpha average and FRUL, which you can enter here for this test. So these are the two characteristics: collector efficiency, collector loss coefficient, and collector efficiency factor. Now if you these two characteristics of a collector we obtain from the test. Now this is called the stagnation efficiency of the collector. So if you hit, this is a y-axis, it is a y-intercept. Okay, so at this point there is no TFI, there is no TFA. So if there is no fluid, if TFI TA is equal to 0, here at this point all are 0, TFI minus TSA, TA and all. So if the collector is not in the collector fluid is not circulated, then what would be the maximum efficiency? So this is called a stagnation, sometimes called a stagnation efficiency. Okay, so this you can extract in actual cases of test setup, you get the points from here. Okay. So in the above equation, in this equation you can see tau alpha average. Now what does this tau alpha average indicates? The tau alpha average indicates effective transmittance absorptance product for normal incidence. Okay, which is near to the solar node. In order to correct now, what Indian standards prescribe? Indian standards prescribe to undertake the testing of the collector at different incidence angles from say 15 degrees, 30 degrees, 45 degrees, 60 degrees. Okay, apart from 0 to 15. Now, so in order to characterize the collector performance early and late in the day, when the angle of incidence of the beam is high, a term which is called incidence angle modifier k tau alpha is defined. Now this k tau alpha is defined as the ratio of transmittance absorptance product at any incidence angle, that is tau alpha, by transmittance absorptance product at the normal incidence. So this value we have, this value we don't have. Now how to evaluate the value of incidence angle modifier? For this expression is used, which is 1 minus BO into bracket 1 by cos theta minus 1. Now BO is the incident angle modifier coefficient. For single glass cover collector, BO is equal to 0.9. Now we can see, just for the sake of illustration, suppose theta is 60 degrees, incidence angle is 60 degrees. Now cos 60 is 0.5. So 1 by 0.5 is 2. Okay. So this 2 minus 1 is 1. Now B0, if we take 0.1, so 1 into 0.1 is 0.1. So 1 minus 0.1 is 0.9. So the value of incidence angle modifier at theta 60 degrees is equal to 0.9. Now this 0.9 multiplied by, now this 0.9 has to be multiplied by this tau alpha average. Now tau alpha average is, suppose for example it comes out to be say 0.78. Now 0.78 is at normal incidence. So this has to be multiplied by k tau alpha 0.9, which we have obtained. So 0.78 into 0.9 will be the FR tau alpha at the desired angle. Okay, so that's how the incidence angle modifier has to be taken into consideration. Another test besides thermal performance test is the most important test prescribed by the Indian standard. Now the second test which is recommended by the Indian standard is time constant test. Time constant is a measure of the heat capacity of the collector. Okay, how a collector responds to the change in the input and output conditions. Now what collector is taking as input? It is taking fluid as input. It is taking radiation intensity as input. Now if either collector fluid inlet temperature is changed or radiation intensity is changed, in how much time it responds, that time constant describes. Okay, so that capacity is described by the time constant. So time constant is defined as the time required for the exit fluid temperature TFO to change by a prescribed amount when the collector is subjected to a step change in the incident solar radiation or in the inlet fluid temperature. Now IS 12933 part 5 prescribes to vary the inlet fluid temperature rather than solar radiation intensity, because solar radiation intensity is a parameter which is not in a manual control. That's why Indian standard doesn't specify changing the solar radiation intensity in time constant test. So now how to conduct this time constant test as per IS? The heat transfer fluid is circulated through the solar collectors and the inlet fluid temperature is adjusted close to the ambient temperature as possible. Okay, we have already discussed how to vary the inlet fluid temperature with the help of storage tank and with the help of heat removal. Okay, so this inlet fluid temperature is adjusted close to the ambient temperature as possible, preferably within plus minus 1 degree Celsius. For example, suppose the ambient temperature is read as 27 degrees Celsius. Then the collector fluid inlet temperature may be adjusted to say 28 degrees Celsius. Okay. Now the steady state and test conditions are maintained. Now this TFI must be maintained at 28 degrees Celsius. Ambient is showing 27 degrees Celsius. Now the incident solar energy is then abruptly reduced to zero by shielding the collector. So we have to pull a cover over a collector. So by shielding the collector from the sun by using a white opaque cover. Now the cover shall be suspended off in such a way, so it should not be just put on. The cover, plastic cover should not just be put on the collector so that airflow and all is restricted. No, the cover shall be suspended off in such a way that the ambient air is allowed to pass freely over the collector as prior to the use of the cover. So the cover has to be just held at a height over a collector. So the collector is needed to be shaded. The following, now in this condition, following parameters shall be measured during the test. Collector fluid inlet temperature TFI, which is maintained, collector fluid outlet temperature, and then surrounding air temperature. Now the measurements are continued until TFO T minus TFI by TFO initial minus TFI becomes, this ratio becomes less than 0.3. Okay. In this in the above expression, what is TFO initial? TFO initial is temperature of heat transfer fluid leaving the collector at the beginning of the time constant test period. Okay, and TFOT is the temperature of heat transfer fluid leaving the collector at a specified time t. For example, we will take an example. I have already said that ambient temperature is 27 degrees Celsius and then TFI we are maintaining 28 degrees Celsius. Now, for example, suppose TFO is 32 degrees Celsius. Collector fluid outlet temperature initially at the first instant measure is 32 degrees Celsius. Now 32 degrees Celsius minus 28 degrees Celsius is 4. Now after 5 minutes of time, this collector fluid outlet temperature is naturally is reduced because it is covered, the collector is covered. So suppose it is reduced to 29.5. Now 29.5 is a TFOT after 5 minutes. And TFI remains the same, 28. So 29.5 minus 28 is 1.5. Now 1.5 divided by this difference is 32 minus 28, 4. So 1.5 by 4. So it comes out to be say greater than 0.32. So this ratio comes out to be say 1.5 by 4. If we just perform this on a calculator, it comes out to be 0.38 or near 0.4. So again we have to wait till we get this ratio less than 0.3, that is 0.29 and all. So the actual time constant is the time required for the quantity on the left hand side of the above equation to change from 1 to 0.368. Okay, but the Indian standard wants this time constant to be evaluated for 0.3. So at which time you get this ratio 0.3. Now in our previous illustration example, I said that after 5 minutes we get this ratio as 0.4. Now after 7 minutes and say 10 seconds, we get this ratio to be 0.29. So in that case we can say that the time constant of the collector is 7 minutes and 10 seconds, that is 430 seconds. So that's how time constant is evaluated. Now besides the time constant test and besides the thermal performance test, for a collector to be allowed for manufacture, the Indian standard has prescribed a more number of quality parameter tests for the flat plate collector. So these tests are mandatory for a flat plate collector manufacturer who intends to manufacture the flat plate collectors on a mass scale and who plans to sell the collector in a commercial market. Now next, the test prescribed is outdoor no flow exposure test. Now this test intends to evaluate the durability of a solar collector by inspecting it after a specified period of 30 days. 30 days outdoor no flow exposure. So you keep the collector for 30 days and you maintain you measure the solar radiation intensity. It has to be 4 kilowatt hour per meter square, 4 kilowatt hour per day has to be the solar radiation intensity for those 30 days. And then you just check if the collector is fine in its appearance for this outdoor no flow exposure test. So how it behaves to no flow and exposure for 30 days. That is the purpose of outdoor no flow exposure test. Next test is static pressure leakage test. The purpose of this test is to ensure the integrity of the liquid collectors to withstand the pressure which it might meet in the service. So static pressure leakage test is that you just place a hydraulic pressure device which generates the pressure, and then the outlet of the collector is closed, and then you go on increasing the internal pressure on the tubes of the collector and then measure what pressure, prescribed pressure, whether it sustains, the collector tubes sustain the prescribed pressure or not. So that is a static pressure leakage test. External thermal shock test. This test intends to assess the capability of a solar collector to withstand thermal shocks externally, which might generate when it gets exposed to sudden rainstorms or hot sunny days. On hot days, suppose it's say today is 28th or 27th of May. Okay, so on 27th of May, the ambient temperature is say 43 degrees Celsius. Now at 3 o'clock in the afternoon, now suddenly the clouds gather in the sky, and suddenly the hailstorm starts, and the ambient temperature drops down from 43 degrees Celsius to say 29 degrees Celsius. In that case, does the collector be stable? So this is a thermal shock to the collector, external thermal shock to the collector. So whether it withstand that external thermal shock or not, that is tested in the simulation or in an actual test platform. Then next test is internal thermal shock test. So this test intends to assess the capability of a solar collector to withstand thermal shocks arising from sudden intake of cold heat transfer fluid on hot sunny days. So again, on a hot sunny day, means on 15th of May or say 16th of May, when the solar radiation intensity is of the order of say 800, 900, 950 watt per meter square, then in that case, if the collector is brought in operation, and then at that time the collector fluid inlet temperature is say cold, so 25 degrees Celsius. In that case, the internal structure of the collector experiences the thermal shock. So does it sustain that thermal shock? That is tested in the internal thermal shock test. So this situation may be encountered when an installation is brought back into operation after a period of shutdown, while the collector is at its stagnation temperature. Okay, so after this internal thermal shock test, rain penetration test. So this test is intended to assess the extent to which collectors are substantially resistant to rain penetration, heavy rain penetration. So suppose heavy rains are happening. So is the water leaking in the collector? How seals are provided? How all those fittings are provided? The quality of the fittings and all. That is tested under this test. So they shall normally not permit the entry of either free falling rain or driving rain. Collectors may have ventilation holes. They must have ventilation holes and they must have drain holes. But those holes must be provided in such a way that they will not permit any entry of the driving rain. So rain penetration test is for this purpose. Impact resistance test. So this test assesses just mischievously if somebody drops a stone on the collector. So does the glass break? Does the collector gets bent or dented? So that impact resistance test is for this purpose. So this test assesses a collector for its tolerance against the effects of heavy impacts of the object, such as those caused by petty vandalism, mischievousness, or by hailstones So sometimes hailstones also fall with a very great impact on the collector, so that it should sustain that impact of hailstones. So this test is for sustaining the impact. So 8 number of tests are prescribed here. Now you can see the fixtures at Solar National Institute of Solar Energy, Gwalpahari, which is also a testing center for collectors. So these fixtures are built for testing the collector as per Indian standards. So you can see in this fixtures, in this fixture, this collector is mounted, collector to be tested is mounted, and then you can conduct the time constant test here, thermal performance test here, and then internal thermal shock test. So 3 tests you can conduct on this fixture. So there can be a very good project in your institute to build such type of a fixture for testing the collectors. Similarly, this is a fixture for rain penetration test setup. So collector is placed, it is fixed on these supports, and then showers are allowed. So water shower is allowed over this and below the collector to test the rain penetration. And here the external thermal shock. So this test setup is for a fixture is for testing the collector for external thermal shock. So it will be a great project also for the students to build such type of fixtures for test setup, and again to conduct the experiment. That can also be a very good project. Now this is again the test setup for no flow. Okay, outdoor no flow exposure. So this is the first test, outdoor no flow exposure test for 30 days. So this is a fixture. The collector is kept on this platform and then it is tested for that. So these fixtures are fabricated, and these fixtures are manufactured for testing the collector as per BIS. So this discussion continues, and we will attempt some numerical examples on testing and characterization of flat plate collectors, which will give you a practical flavor of the testing and the details or the micros of the testing. Thank you.